All right, so it's great to be back in Princeton. Yeah, so today I'm going to talk about periods of quaternionic Shimura varieties. So the basic setup is the following. I start with a totally real field F. Say degree d over q. And I start with small f, a holomorphic Hilbert modular new form. And say the weights are, I assume the weights are motivic, so the weights are k1, k2 through kd, where the ki satisfy a congruence condition. And these are all congruent to each other mod 2. Okay. All right. Now, so one invariant that you can attach to such a form is the Petersson inner product of f. And one thing that you can do is you can start with a quaternion algebra over f. And it's sometimes the case that you can transfer this form f to a form on this quaternion algebra by the Jacquet-Langlands correspondence. And so the Jacquet-Langlands correspondence gives precise criteria for which you can transfer f to some form fb on the quaternion algebra B cross. So I think of f here as a form on GL2 AF, and you might be able to transfer f to a form on B cross. And then the question is, how are these Petersson inner products related as B varies? So there are several issues. So first, so this you can define just as the integral over B cross A or B cross Q of FB bar with respect to the Tamagawa measure, for example. Okay. Now, there's some issue of normalization. I'll talk about how you normalize these forms in a bit. Okay. But why is such a question interesting at all? So there are two reasons why you might want to understand this. The first reason is that these periods naturally occur when you study special values of L functions. So there are all these conjectures about special values of L functions that are formulated in terms of certain periods. When you try proving them, you often end up with other periods, not the periods that are in the conjecture. And then you need to relate periods. So that's one reason this is interesting. The second reason is these has to do with the Tate conjecture. The point is that you can associate to F Galois representations. Now, you expect a two-dimensional Galois representation. And one way to construct a two-dimensional Galois representation is to take a quaternion algebra B, which is ramified at all but ramified at say split at V1 and unramified and ramified at V2 through Vd, where V1 through Vd are the infinite places, and then take a Shimura curve associated with this. Associated Shimura curve. And if such a quaternion algebra existed, then you would be able to construct the Galois representation in the cohomology of that Shimura curve. Right? But more generally, if you take so let's sigma infinity be the set of infinite places of F. And let sigma infinity b be the set of infinite places where b is ramified. then if you look at there's an associated Shimura variety which I'll call x sub b, and you can construct a Galois representation there, but what you get is not a two-dimensional representation, but a representation that is 2 to the d prime dimensional, where d prime is the cardinality of the set sigma infinity minus sigma infinity b. So for example, if b is M2 of f, right? So you're looking at Hilbert modular varieties, then you get not a two-dimensional representation, but a 2 to the d dimensional representation. And this 2 to the d dimensional representation is something like a tensor product of the various representations that you would get from different quaternion algebras that you would get by replacing v1 with one of the vi's over there. Okay, so so what this means is that if you look at the places, so this deep, if you look at the set of places, say let's say v1 through vd prime is the set b sigma infinity minus sigma infinity b, then there's you can look at this variety x sub b and you find a 2 to the d prime dimensional Galois representation there. On the other hand, you could look at Shimura curves corresponding to these different places. I'll call them x sub vd prime, right? And you can also get a 2 to the d dimensional representation by just taking the tensor product of these things. And the Tate conjecture will predict that there's a cycle on this big product that realizes this equality of Galois representations. Okay. So we don't know how to construct these cycles, and it's a very interesting problem to construct these algebraic cycles. But if you knew the Tate conjecture and you knew there was such an algebraic cycle that realized this isomorphism of Galois representations, then you would have an isomorphism of Hodge structures, and that would translate into some relation between periods. So you can ask yourself the following question: can you prove these period relations directly without knowing that these algebraic cycles exist, for example? Yes?
I'm sorry, there's an issue of the reflex field. You never said that.
I am not
Galois representations
right over what. So I don't want to even say that. Right. Yeah. So that's right. So this is the tensor induction of those representations. But if you're working over Q bar, for instance, then there's no problem. Right. So right. So the point is that the Tate conjecture predicts period relations, and you might try to prove the period relations directly, and maybe hopefully one might get some ideas on how to maybe construct these algebraic cycles. So that's one goal of this project. Okay, so let me formulate this somewhat more precisely. So just remind you again. So sigma infinity is the set of infinite places of f, right? And right. So here's the formulation. Right. So I start with this f, which is a Hilbert modular form, right? And I'll call pi the corresponding representation, automorphic representation of GL2AF. And I'll let B be a quaternion algebra that f transfers to, or that pi transfers to. I'm not assuming parallel weight 2, right? Okay. And recall there's a condition that B has to satisfy for this to happen. And the condition is that B can only be ramified at places where pi is discrete series. Okay? So there's some condition given by Jacques Lagrange. Right. And so you can look at pi b, the corresponding representation on B cross. B cross AF. And what I want to do is pick a form f sub b inside pi sub b, which is normalized in some way. Okay? So so just to fix ideas, let's just think of the parallel weight 2 case. The weight is 2, and suppose that the level is some n, which is square free. Okay, then you can pick such an FB to be a new form, because I'm assuming that the level is square free. This is well defined up to scaling. Okay? And then there's an issue of how to fix the scalar. Now, if you work with Hilbert modular varieties, then you have Q expansions, and so you can there's this natural way to fix the scalar. But if your quaternion algebra is not M2 of f, then the associated Shimura varieties are compact, and you don't have Q expansions any longer. So there's an issue of how to fix these scalars. But the point is that you can still think of f sub b as a section of a vector bundle more generally, but in this case a line bundle, right? And the Shimura variety has good reduction outside a finite set of places. So if you're outside, if you fix a prime p, for example, so that p equals a prime, not dividing the level, then you can use the integral model of the Shimura variety x sub b to fix f sub b up to an algebraic number that is a p unit, that is so up to an algebraic number that is a unit at all primes above. Okay. You can be more precise. You can work over specific number fields if you want, but then I have to talk about the reflex field and so on, which I don't want to get into. But the point is, you have an integral model, and you can, at least if you work outside of the bad primes, you can certainly fix this up to an algebraic number that is a p unit. And so you can now ask. So now you can really ask this question: how are all of these related? Okay. So Shimura was the first person to study this question, and Shimura, I'm going to explain Shimura's conjecture. Okay. So in the early 80s, Shimura made a conjecture which essentially follows from the Tate conjecture, but the conjecture is the following. There exists a function which I'll call C from the set of infinite places to the complex numbers, sending V to C sub V, okay, with the property that such that if I take the inner product f sub fb fp, this is equal up to algebraic. So this symbol will mean the ratio is algebraic. Okay. The product of those CVs where b is split at v. In other words, up to algebraic factors, the Petersson inner product only depends on the set of infinite places where your quaternion algebra is ramified or split. Okay? And associated to each infinite place, there is this invariant C sub V, so that if you want to compute the Petersson inner product on any given quaternion algebra, you just look at the places where it's split at infinity and take the product of those CVs. Okay? One way to think about this is that there are lots and lots of different quaternion algebras. Well, there are at least 2 to the d of them, maybe more, right? And on the other hand, there are only d such CVs. So this is telling you there are lots of interesting relations between these periods and the different quaternion algebras. Okay. So Shimura was able to prove part of this. So Shimura in fact showed, for example, that if B1 and B2 are complementary quaternion algebras. So what I mean by this is the ramification at infinity is complementary. Then what you would expect, well, then you would expect that when you take the product these guys, well, what you should get is the product of all the CVs, right? Now the product of all the CVs should be equal to the Petersson inner product taken on GL2. Right? So this is equal to. So Shimura is able to show this, for instance. If we take 2 complementary quaternion algebras, then the periods match up right. Okay. And Michael Harris later essentially proved this conjecture, and he proved the conjecture under a certain hypothesis which I'll call star. And this hypothesis is that there exists at least one finite place at which pi v is discrete series. So I take my automorphic representation pi is a restricted tensor product over all the places, some local representation pi v, and as Harris proves this conjecture under the hypothesis there's at least one finite place at which is discrete series. And the reason he needs this hypothesis is because his proof is an induction on the set of infinite places that are ramified, and so since this is an induction, he needs to know that given any set of infinite places, that is any set of infinite places, there is a quaternion algebra ramified exactly at that set of infinite places to which f transfers, and so he needs the flexibility of having a finite place, right? Yoshida used some tricks using base change, was able to remove the star if all the weights are at least 3. But so there's one case, for example, the parallel weight 2 case of this was still open, right? Because in the case when there's no finite place which is discrete series. Okay? So what I want to talk about today is the following. So there are two things you could do. One thing is you could think about is you could ask for something more precise than this. You want to replace this q bar cross by something more precise, right? So one thing you might try to do is replace it with a number field. Right? You might want rationality results over a specific number field. The other question, so that's one issue, rationality. And the second issue is, well, since we've fixed our fp up to p units, you can ask, can I make a conjecture that's good up to p units? Okay, so there's an integrality question. These questions are somewhat orthogonal to each other, and today I want to focus on the integrality question. So what I want to explain is a different approach to this that will give a new proof of this theorem of Michael Harris, and in fact this new proof will get rid of that condition completely. So you would. Sorry, say that again.
In what sense are they?
Because well, they're orthogonal in the sense that rationality and integrality are two different questions. You can. Neither one tells you much about the other, right? I mean, this is something that you can work over q bar to decide integrality. Well, so they're both delicate in different ways, and you have to be.
When you prove integrality, you don't control the.
You can control rationality exactly, but it's harder to control that, right? And when you prove rationality, it would be hard to control integrality and so forth. So, right. For example, Michael Harris thought at various points that he could prove rationality using his methods, but there are so many steps involved in it, it's difficult to keep track of what's happening. So, all right. So I want to talk about the integrality question today. Right? Now, the integrality question is already interesting over Q, right? And so I want to explain what happens for weight 2 forms over Q, and then we'll use that to predict what should happen for over totally real fields. Okay. So here's the setup over Q. So suppose f is Q, and we'll keep it really simple. Let's say f is a modular form of weight 2 and square free level n. Say the Fourier coefficients are in Q. So f corresponds to an isogeny class of elliptic curves. Over Q. Okay. And so let's say that B is, so for now, let me think about the indefinite case. So let's say that B is an indefinite quaternion algebra with discriminant n minus, discriminant b equal to n minus dividing n. So since b is indefinite, n minus is divisible by an even number of primes, and I can write n as n plus times n minus. Okay. So now I can take the Shimura curve x sub b, where I take an Eichler order. So this is the Shimura curve associated to an Eichler order in B of level n plus. And by the Jacquet-Langlands correspondence, f will transfer to a form fb on x sub b, and the question is how are ff and f sub fb related? Right? So how are these related? Okay. Now, so you remember that you have x naught of n, right? And f corresponds to an isogeny class of elliptic curves. In this isogeny class, you can find a so-called strong Weil curve, namely a curve such that the induced map, there is a map from x naught of n to e, which is of minimal degree. Okay. And likewise, you have x sub b, and there's going to be possibly some other curve in the same isogeny class, which I'll call e prime, such that that is a strong Weil curve for x sub b. Okay. And you have these are modular parameterizations. I'll call these phi and phi prime. Right? Now, what we're interested in is these Petersson inner products up here. You can if you start with a Néron differential here and pull it back, then what one knows is that you essentially get f, you get 2 pi I fc dz times some constant, the Manin constant, which you know to be 1 or 2, so we can ignore this if you're working at an odd prime, for example. And likewise, there's a similar result over here, which you can prove by essentially the same methods, namely that if you start with a Néron differential here and pull it back, then you get 2 pi I fp zds. So if you want to relate the Petersson inner products over there, what you want to do is relate the integral of omega e wedge omega e bar over here to the integral of omega e prime wedge omega e prime bar here. And then you want to know what the degrees of these things are and what the ratio of the degrees is. Okay? So what you get now, E and E prime are isogynous, so I can pick an isogeny here, right? And let's suppose that P, the prime P that I'm interested in, is not an Eisenstein prime for F. So what this means is that the Galois representation, the mod P Galois representation associated to F, the representation of the P torsion of either E or E prime, is irreducible. Okay? If P is not Eisenstein, then you can pick this isogeny to be of degree prime to P. Okay? So that will tell you that these two guys are related up to P units. So these guys are equal up to P units. So if you compare the degrees, if you take this ratio is essentially equal to the ratios of the two degrees, the degree of phi divided by the degree of phi prime. Now this is, how should one think of this? One thing that one knows is that this degree counts congruences between f and other forms, okay, on x naught of n. Likewise, the degree here should count congruences between fb and other forms and forms that occur on x sub b. However, there are some forms that occur on x naught of n that don't occur on x sub b. So the ratio should count congruences between between f and other forms on other forms that don't appear on x sub b. Okay? These are the so-called level lowering congruences. So in fact, let there's a result of Ribbit and Takahashi that says what this is very precisely. So it says again up to Eisenstein primes. So up to Eisenstein primes. It says that this is the product of CQ or Q dividing n minus, where CQ is the order of the component group of the neuron model of E at Q, say, or E prime at Q. It doesn't matter because up to Eisenstein primes, if you're looking at an Eisenstein, if you're looking only for P divisibility for P not an Eisenstein prime, the orders of these component groups are the same. Okay. So there's a very precise result that says that the ratios of these degrees is the product of some orders of component groups. So firstly, it's integral, right, because it's the order of a group, and secondly, one knows that if the P divides CQ, if and only if P is a so-called level lowering congruence prime, namely if F is congruent to some G mod P, where G is a form of level dividing n over Q. So in other words, these CQs count exactly level lowering congruences at Q. Okay. So what we want to do is put together this very precise result over Q with Shimura's conjecture, right, and see if we can make a conjecture over totally real fields. Okay. So let's just stare at this. Right. Now I want to write FB. So I can write this way. Well, I write this as FF divided by the product of the CQs. And to say Q divides n minus is to say exactly that Q divides the discriminant of B. Right? And FF, by the way, I can write also as the adjoint L value at once, so I might as well do that. This is this guy divided by the product of the CQs. Q divides the discriminant of B. On the other hand, stare at Shimura's conjecture, which I've erased, but I'll write it again. Remember what Shimura's conjecture said. It said that FP, this is for a totally real field, up to algebraic factors, is the product of those CVs where V is in sigma infinity and V is B split at V. Okay. And you can write this as the product of all the CVs, so over all V in sigma infinity, but divided by the product of those guys where V is ramified. So V in sigma infinity, V divides the discriminant of B. Okay. Now, if Shimura's conjecture is true, then the ratio on the top is the adjoint L function up to algebraic numbers. So again, up to algebraic numbers, this is the adjoint L value, because this is the Petersson inner product of the Hilbert modular form, divided by the product of those CVs. V is in sigma infinity, and V divides the discriminant. Okay. All right. So now you just stare at these two conjectures. So this is something very precise that happens over Q. Right? This is something that holds up to algebraic factors over totally real fields. Over here you have, because you're working over Q and it's indefinite, what you have is a product over the finite primes which are ramified. Right? Well, here you're only working up to Q bar cross, so you're only looking at the infinite primes. Okay? So it's a very natural conjecture that just falls out of this, which is the following. Suppose back to the totally real case. The conjecture is going to be the following. there exists a function which I'll call C. Now from where? So let me make a definition. So let sigma pi be the set of places V such that pi V is discrete series. Okay? The set of places is relevant because of Jacquet-Langlands. Jacquet-Langlands tells you that you can transfer to a quaternion algebra B exactly when the set of ramified places of B is contained inside sigma pi. Okay? So the conjecture should be there's a function C now from sigma of pi to C cross such that if I take this Petersson inner product, then this up to p units because of fixed sum prime p is equal to the adjoint L value divided by the product of those CVs where V divides the discriminant of V. Okay. So in other words, there should be invariants attached not just to the infinite places, but to all the, which are of course all discrete series for this representation, but all the finite places which are discrete series, such that you can say exactly what happens integrally. Okay? So the expectation should also be that so just let me remark that first we'd expect that for V infinite, the C sub V's are transcendental and in fact all algebraically independent. On the other hand, for finite V's, for finite places V, what you'd expect is that the CVs are all algebraic or algebraic integers. Algebraic and I guess p integers because I'm only normalizing things up to p units. Okay? And further that these should count congruences and count level lowering congruences at V. Okay.
I'm just a little bit confused.
Yes.
So say you just had infinite places.
Yes.
You're saying these CV are algebraically independent of each other?
Of each other, right? That's yeah. Except if the form is special in some case. For example, so unless the form is special, for example, if f is a base change, from a smaller field, right? I'm not saying I can prove it, or I just say this is what you'd expect, right? For example, if you take a variety over a number field f, and you take different complex embeddings of this and look at periods of the same differential form, you shouldn't expect any relations between these periods. So.
But is this precise? Does it
No.
follow from Botanics conjectures?
Oh, I have no idea. Yeah. I have no idea. I'm not going to say anything about this transcendental question. I'm interested in the algebraicity issue. Yeah.
Special should include CM forms?
I don't think so. I think even for CM forms, you should see at all places you should expect different things. Right. But if it's a base change, then you expect relations. Okay. Right. So in what cases do we know this conjecture? Certainly from what I said, we know this conjecture. We know this for indefinite quaternion algebras over Q. And in fact, you can also prove the definite case. So we know this for quaternion algebras over Q when the weight is 2. Okay. And towards the end of the talk, I'll show you a slide with that'll show an explicit example where you actually see this happening.
So what does remark 2 mean when pi v is super?
Say it again. What is what?
When pi v is super cuspidal,
Yes.
you have still this
You should.
interpretation.
Yes. Yeah. You should still have this interpretation in terms of congruence. Okay. So now I'm going to switch a little bit. I'm going to tell you about a new method to think about this problem. So everything henceforth is joint work with Ichino. Oh, sorry, this conjecture appeared first in an article I wrote in an AIM conference volume on Eisenstein series. It's 2008. Okay. All right. So I now want to talk about joint work with Ichino. This is, I guess I should say, ongoing joint work. I'm going to talk about a different approach to this problem of proving these period relations. It's different from the one that Harris had, and that seems to expose a certain structure which would be useful to study these integrality questions. But it also turns out to give a new proof, and it'll prove the algebraicity relations without this condition star, that at least one finite place has to be a discrete series. So I'm going to switch a little bit in this. I'm going to talk about a completely different problem that we were thinking about that led to this. So the different problem has to do with the relation between periods and L values. Okay. So there are these famous formulae that relate period integrals to L values. And there are two famous formulae. The first is that of Tunnel-Saito and Watson. And what this formula says is the following. Remember, I have this f and I have this pi, right, on GL2 AF. Okay. F is totally real. Suppose that E is a CM field. E is a CM field. E over F is CM. So E is degree 2 over F. And chi is a Hecke character of E, an algebraic Hecke character. Say an algebraic. Okay. And suppose that if you take the central character of F, which I'll call omega sub F or omega sub pi, and the central character of chi, suppose the product of these guys is 1. So the central character is just the restriction of chi from the ideals of E to the ideals of F. Okay. Then the theorem of Tunnel-Saito and Watson says the following, that there exists a quaternion algebra B that pi transfers to, and a form F sub B on B cross, right, and an embedding of E in B, such that if you look at, so therefore E cross embeds in B cross. So you can start with, you can take your form F sub B, which is a form on B cross A, and restrict it to E cross A. And integrate this against chi. Okay? And the formula of Walsh-Burchet says that the square of this integral up to some explicit normalization factors, so the dot will mean some explicit normalization factors, is going to be the L value at 1/2 of the Rankin-Selberg of F and the representation pi chi of GL2 of AF associated to chi. Okay? There are some explicit normalization factors which I'll ignore. I just want to explain the structure of the formula. The structure of the formula says there is a quaternion algebra. In fact, it's a unique quaternion algebra, such that when you take this form on the quaternion algebra and take this period against chi and square it, you get one of these Rankin-Selberg L values. Okay? And which quaternion algebra is it? How do you identify it? You identify the quaternion algebra in terms of epsilon factors. So B is identified by an epsilon factor condition. Okay? which I won't write down explicitly. The key point is that there's a unique quaternion algebra. So that's one formula. The other famous formula is the triple product formula. So let's so the second one is the triple product, which is the following. It says if you have 3 automorphic representations, pi1, pi2, and pi3 on GL2AF, such that the product of the 3 central characters, so omega pi1 times omega pi2 times omega pi3 is trivial, then it says something very similar. Then there exists again a unique quaternion algebra so I should have said one thing here. So in this condition, so there's something I omitted. You also need that the epsilon factor here has to be 1. So in addition to this, you want this epsilon factor of this L function, so epsilon f chi, to be plus 1. Okay. Otherwise, this doesn't happen. Likewise here, suppose in addition to this condition, the product of the central characters be trivial. Suppose that the epsilon factor of pi1 tensor pi2 tensor pi3 at 1/2 is plus 1. Okay. Then it says similarly that there exists a unique quaternion algebra B such that the 3 representations pi1, pi2, and pi3 all transfer to B. Okay. And there are forms which I'll call f1, f2. There exists f1, f2, and f3 in I'll just say fi in pi sub b, pi sub ib, with the property that if you take the integral of f1 times f2 times f3 and square this, then again up to explicit factors, this equals the triple product L value. Half of. Okay. So this formula was first proved by Harris and Kudla, but then made more explicit by Watson. And there's also papers of over Q, and then Ichino and Ikeda also have articles on it. Okay. All right. So the question that we're thinking about is, okay, you have these 2 different formulae relating period integrals to L values. Are these formulae related in some way? Okay. Now this is a degree 8 L function, while those are degree 4 L functions. So you would want to put yourself in a situation where this degree 8 L function factors as the product of 2 degree 4 L functions. Okay. And one case that happens is when you take pi2 and pi3 to be associated to Hecke characters of the same imaginary quadratic field. So that's or same CM field. Right.
These 2 formulas have nothing to do with algebraicity. I mean,
yes.
Pi needn't be algebraic.
Sure. Okay. So now let's suppose that pi1 is our pi, and we have this the CM field E, and let's say pi2, and we have 2 characters which I'll call eta1 and eta2, Hecke characters of E, and let's say pi2 is the representation associated with eta1, and pi3 is the representation associated with eta2. Okay. And now let's take the Rankin-Selberg, or the triple product pi1 tensor pi2 tensor pi3. Right? And this you can check easily equals ls pi chi1 ls pi chi2, where chi1 and chi2 are related to eta1 and eta2 by the relations chi1 equals eta1 eta2 and chi2 equals eta1 eta2 rho, where rho is the non-trivial Galois automorphism of E over F. Okay. So you can ask the following question. Let's put ourselves in a situation where the signs are all plus. right? Then you have one formula for this guy. The central value L half is some period integral in a quaternion algebra, and likewise you have formulae for these two, right? Except you're going to get 3 different quaternion algebras in general, right? So this is going to happen in some quaternion algebra B, and this is going to happen in B1, and this is going to happen in B2, and B, B1, and B2 are identified by epsilon factor conditions. Okay? So you know exactly what they are. So there's going to be a relation between B, B1, and B2, right? You can, somebody want to guess what the relation is? It's that B equals B1 times B2 in the Brauer group. Okay. So you have 3 quaternion algebras, but they're related in this way, and you have some such formula in each of these. So this is some period integral squared, and this is some period integral squared times the period integral squared. Okay. So you can ask yourself the following question: can we prove this relation between the period integrals directly without going through these formulae, for example, right? And without the squares, right? Can one show this directly? Okay. So I want to explain how one can do that, and that will relate up to the old problem that I was talking about. Okay. So the key construction. So here is the key construction. Okay. So recall that here what we know is that this is a period over E, right? So we know E embeds in both B1 and B2. So let's fix these embeddings. Okay. And we can write B1, for example, as E plus EJ1, where this is an orthogonal complement to the norm form, for the norm form, and likewise B2 is going to be E plus EJ2. So J1 and J2 both have trace 0, right? So trace 0, and we'll say J1. Suppose that J1 squared, I'll call this J capital J1, and J2 will be J2 squared. These live in the ground field F. Okay. Now you can think of B1 as a 2-dimensional E vector space in this way, right? So B1 and B2. So B1 is a 2-dimensional right E vector space. And in fact, you can make this into a Hermitian space in the following way. You just define a form. So there are projections. So I'll call PR the projection onto this coordinate. I'll call PR1. The projection onto this coordinate I'll call PR2 here. So you just define this to be, so in fact each BI is a 2-dimensional right E space. And I make it into a Hermitian space with the following form. I just take PRI of x, y star, where star is the main involution. Okay, maybe I want x star y. Okay. So so I have two right E spaces, right? And I have a Hermitian form in both of them. Let's take their tensor product over E. Okay. And I take the tensor product of these two forms. So this becomes a 4-dimensional right E space with a Hermitian form. Okay. Now, so the Hermitian form is going to be the product. So it's just going to be given with the product of the two forms. So x1, y1, x2, y2. This is Hermitian, but I can make this Q Hermitian by just multiplying it. So I pick some element which I'll call alpha. So pick alpha in E of trace 0. That's non-zero. And multiply this by alpha. Okay. And so this has the effect of changing this Hermitian form to a skew Hermitian form. Okay. So this is skew Hermitian. All right. Now, remember this is a right E space, but it turns out that we can make, I'll call this V. Okay. So remember that E embeds in both B1 and B2, and B is the product of B1 and B2 in the Brar group. Right? So E embeds in B as well. So let's fix such an embedding. Okay. And now we can make V into a right B space, in fact. Okay, in the following way. So B1 and B2 are both given by are given in this way, right? As in terms of J1 and J2. And if you think about how you can write down B, well, E embeds in B, and here's a model for B. You can write B as E plus Ej, where J squared is J1, J2. And the obvious relations hold, namely x times j is jx bar for an element x in E. So how do I make V into a right B space? I already know how E acts. I just need to tell you how this little j guy acts. Okay? Right. And so I make it act in the following way. I look at all the basis vectors. So on 1 tensor 1, I make this act by sending it to J1 tensor J2, J1 tensor 1. Make this act by capital J1 times 1 tensor J2, and so on. So 1 tensor J2, capital J2, and J1 tensor J2, it's J times 1 tensor 1. Okay. And it's straightforward, but a little tedious to check that in fact this gives a right action. So what I have now is a right B space, right? But it's now two-dimensional as a B space. Okay. And in fact, one can write down, which so it turns out that one can write down a B skew Hermitian form on V, which I'll call bracket, such that the skew Hermitian form, the E skew Hermitian form, is just the trace of the B skew Hermitian form. Okay? So what I have now is a two-dimensional B vector space with a skew Hermitian form. Okay? So let's look at the unitary similitude group of this. Okay? So now, what is this group? Well, you have actions of B1 and B2 on V on the left, right? And you can check that these in fact land there. So if you look at the connected component of this group, it turns out to be exactly B1 cross B2 cross mod F cross. Okay. On the other hand, I can take W to be just B with the usual Hermitian form, namely I just define xy to be x star y. This is a B Hermitian form, and so that's also a B space. And I can look at the unitary at the unitary group GU BW. Okay. So I have two spaces. This is a one-dimensional B space, and that's a two-dimensional B space. And the theta correspondence gives me a lift from this is basically just B cross from here to GU BV 0, which is B1 cross B2 cross mod F cross. Okay. Well, what could this lift possibly be? You're going from B cross to B1 cross B2 cross. This is going to be the Jacquet-Langlands correspondence. Okay. So the first proposition is that in fact this is the Jacquet-Langlands correspondence. And then so it turns out that so you have B cross below, and you have b1 cross b2 cross or f cross, and there's a seesaw pair which I won't write down, but if you just stare at the seesaw pair, what you get is exactly the period relation that I explained before. So there was supposed to be some equality of periods, and so the equality of periods just follows from Kudla's seesaw duality. Okay, but now you face the following interesting question. I have this map. I have this from representations on B cross, the theta correspondence, two representations here. How does that interact with arithmeticity? Okay, so I start with an arithmetic form here, say an integrally normalized form, and then take the theta lift here. What is that? What can I say about the lift over there? Okay, so let's start with, let's say I have some FB over here, right? And I lift this here, and I get FB1 cross FB2. But then I get some coefficient over here, which is some factor, and you want to know what this factor is. Now, one way to analyze this is use the Rallis inner product formula, which tells you what the inner product of the lifted form is in terms of the original guy. So let's say alpha is real, then what you get is alpha squared times the inner product on B1 times the inner product on B2 is what? It is the inner product here times an L value. The L value here turns out to be exactly the adjoint L function. So you get a relation between the Petersson inner products. Okay. All right. Now we expect there's a conjecture that we have for the Petersson inner products in terms of these invariant CVs. So you can just feed that conjecture in here and see what you get. So if you feed that in there, what do you? So each of these guys is supposed to be, this is alpha squared, this is the adjoint L value, divided by the product of the CVs, where V divides the discriminant of B1. This is the adjoint L value divided by the product of the CVs, where V divides the discriminant of B2. And on the right hand side, you get the adjoint L value twice, divided by the product of the CVs, where V divides the discriminant of B. Okay? So you see what alpha squared has to be. Alpha squared has to be the product of the CVs, where V divides the discriminant of B1 times the product of the CVs, where V divides the discriminant of B2, divided by the product of the CVs, where V divides the discriminant of B. Okay? Now remember that B is the product of B1 and B2 in the Brauer group, right? So this is the square of something, namely it's the product of the CVs, so where V is in sigma B1 intersects sigma B2. You get a square there. Okay? So sigma B1 is a set of places where B1 is ramified, and likewise for B2. So you get a so now you see this is what alpha squared should be. So this leads to the following conjecture. If sigma B1 infinity intersects sigma B2 infinity is empty. So if B1 and B2 have no infinite places of ramification in common, well then the only CVs you pick up here are at finite places. And at finite places the CVs should be algebraic and in fact algebraic integers. So I'll call this alpha of B1, B2 is algebraic and P integral. Okay? And if further they have no finite places in common of ramification, then in fact alpha B1, B2 should be a unit. Right? Okay. So now what we've shown is that the previous conjecture, which I imply along with the expectation of what the CVs should be, that they should be algebraic, etc., implies this conjecture. But in fact, you can go back and show that the second conjecture also implies the previous conjecture. So the point is you have to define the CVs, and it's not hard. You just use these relations to define the CVs. So these conjectures are more or less equivalent. Now, This provides a framework to think about this question. And in fact, one thing that we can prove is we can prove this part right now, namely that alpha b1, b2 is algebraic. And once you do that, then you can go back and you get Shimura's conjecture without this assumption that it's some finite place or discrete series. And I think this is some of the right framework to think about these integrality questions also. One problem with integrality questions is that you often want to prove cancellation, and it's very hard to prove cancellation. So it's nice to set yourself up in a situation where you expect something to be a p unit directly, rather than try to prove that two different things divide each other. And so one has some hope of addressing these questions by these methods. Okay, so I'll stop here. I wanted to show one slide, but that's okay. How do I prove this is a?
Using Rallis?
Use Rallis, yeah. Use Rallis, yeah. It's so the proof is, yeah. You have to use Rallis. You analyze this. You analyze the periods here,